Hello everyone. I'd like to thank the organizer of the World of Groupcraft 3 for giving me this opportunity. The title of my talk is Congruence Subgroup of Small Coxeter Group. This is a joint work with Dr. Mahender Singh and Dr. Tushar Kanta Naik. Let us begin. A congruent subgroup for a matrix group G and Z is usually defined as a kernel of this model IM reduction map. So now given a group G, one can define a congruent subgroup via a choice of integral representation. Okay? Let G be a group with a fixed integral representation. Then for any positive integer M, the principal congruent subgroup of level M is defined as the kernel of this composition map from G to GL and Z, then the modulo M reduction map. In case of mapping class group of closed surface, one uses the standard symplectic representation to study the congruent subgroup. We say a subgroup of finite index as a congruent subgroup if it contains some principal congruent subgroups. Then the natural question is to ask for, is every finite index subgroup of a group G is congruent or not? A positive answer to this question helps us in understanding the structure of finite subgroups like subgroup growth and profinite completion, etc. We are interested in answering these sort of questions for Coxeter groups. A group W is a Coxeter group if there exists a set X, yes, such that we have a following presentation. The generating set is the set S, and the defining relation is determined by this exponent Mij, which is nothing but the order of the product of any two generators. We also define that the generators are involutions. So the pair W, S is called the Coxeter system. We say a Coxeter system is rank L if the coordinate of the set S is L, and the Coxeter system is reducible if it can be written as a direct product of two smaller Coxeter systems. To see an example, the symmetric group on n letters has a Coxeter presentation with the generators tau 1 dot dot tau n minus 1, where tau I is just a simple transposition interchanging I and I plus 1. And the defining relations are they are order 2 element, the involution relation. Second relation is a braid relation. And third is what we call as far commutative relation. It means saying that disjoint cycle commutes. Now, by omitting the all relations of type 1 or 2 or 3 or 1 at the time from the preceding presentation, we obtain the presentation of braid groups, twin groups, and triplet groups. For instance, braid group is just obtained from the presentation of a symmetric group by forgetting the involution relation. Twin group is obtained by forgetting the braid relation, and the triplet group is obtained by forgetting the far commutativity relation. The term twin and triplet group were coined by Kavanaugh in his study of K-pi-1 subspace arrangement. For a terminology convenience, we say a Coxeter group to be a small Coxeter group if it has a Coxeter system in which the exponent Mij is either infinity or less than or equal to 3. Quick examples are symmetric groups, and it's the canonical extension. Twin groups and triple groups are small Coxeter groups. There's another family of Coxeter group called right angle Coxeter group. So these are the Coxeter group in which the exponent is either infinity or 2. They are also an example of a small Coxeter groups. Then let's define a Tits representation. Let W be a Coxeter group with the Coxeter presentation. Let V be a real vector space spanned by the set S. So define a symmetric bilinear form on V in this form. Then the linear map defined by in this fashion defines the automorphism of V. Having this terminology, we have the following well-known result that the map rho from the Coxeter group to GLV defined by setting the image of the generator W as sigma I is a faithful representation of W. This representation is called the Tits representation of W. Our first observation is the Tits representation of a Coxeter group is integral if and only if it is small Coxeter group. That is, the corresponding Coxeter system is a small Coxeter system. The proof is basically noticing the entries of the matrix. Okay. So in a view of above lemma, we study the principal congruent subgroup of small Coxeter group using the Tits representation. So our first observation is that the principal congruent subgroups are Thompson free. So since each generator is an involution, the image of the generators are determinant -1 matrix. Therefore, for a word to have a determinant 1, to have a image to have a determinant 1, we need the word length to be of even length. That is our first result. If an element lies in the principal congruence subgroup, then this is of word even length. As a corollary, we deduce that the level M principal congruence subgroup of W is torsal free. Then we have a following result regarding the congruent subgroup property of small Coxeter group. Our result is an infinite small Coxeter group, which is not virtually abelian, does not have a congruent subgroup property. Using this result, we deduce that any irreducible infinite right angle Coxeter group of rank more than 2 does not have a congruent subgroup property. In particular, twin group is an irreducible right angle Coxeter group of rank more than 2. Therefore, twin group does not have a congruent subgroup property when n greater than or equal to 4. And when n equal to 3, we explicitly calculated the principal congruent subgroup. As a consequence, we see that T3 has a congruent subgroup property. Concerning triplet groups, the triplet group does not have a congruent subgroup property when n greater than or equal to 4. If I want to sketch the proof, we just found the finite index free group inside the triplet group. Thus, the following question seems natural in a view of preceding result. Determine the finite index subgroup of twin groups and triplet group which contain no principal congruent subgroups. So in this direction, we have also computed the congruent subgroup of smaller level, which are well-known finite index subgroups. Let W be a right angle Coxeter group, then the level 4 principal congruent subgroup is nothing but the commutator subgroup of W. In case of twin and triplet groups, the level 3 and level 6 is just the kernel of this natural projection map, which we call pure twin groups. And for level 2 congruent principal congruent subgroup or triplet group is the kernel of this natural projection map, which is called pure triplet group. And in a recent work, the quotient of congruent subgroups of braid groups are studied. In a similar direction, we have a following result that if M is not a multiple of 3, then this quotient is just isomorphic to the alternate group AN. And when M is odd and let H be a index to subgroup of this group, the n times the direct sum of Z2, then we have this quotient group, TNM quotient by Tn of 4M is just isomorphic to H. Combining 1 and 2, we have that when M is odd and 3 does not divide M, we have this particular quotient is isomorphic to AN direct product H. So with this, these are the reference. This is our paper. So with this, I will end my talk.